Like a waterfall in slow motion.
Hi, I'm Juha and I'm a hockey player here at USC. I will be going through some physics concepts and examples with you this semester. And remember, just like on the ice, there's no such thing as luck in physics. Just keep your head up and work hard.
Wheelbarrow is the do-it-yourself man's best friend. And why is that? In this problem it is stated that suppose you cannot lift more than 650 newtons. So either we could carry as much weight, or we can provide 650 newtons at the end of the wheelbarrow. Let's call this F, the lifting force. And the question is now, how much can you lift using 1.4 meter long wheelbarrow that weighs 80 newtons, so it has some weight, and the center of gravity is 0.5 meters from the center of the wheel. So here we have the weight of the wheelbarrow. Let's call it weight wheelbarrow. And also the center of the gravity of the load carrying the wheelbarrow is 0.5 meters from the center of the wheel. So we have another force here, so that's the weight of the load. They both have the same center of gravity. And then there's a follow-up question: where does the force come to enable you lift more than 650 newtons? But let's first analyze part A. How much can we lift using this wheelbarrow? This is a static equilibrium situation, so we have to take into account all the forces and torques. And we have one more force missing here, and that is the support force from the ground via the wheel. Let's call it N. And we'll define positive directions like this, up and right, and for torque, our positive direction would be clockwise. We only have forces in the y direction, so we don't have to worry about the horizontal direction. So some forces in y direction, we have FL plus N positive, and then the weights of the wheelbarrow and weight of the load negative. And then the sum of the torques about some chosen point. What should we choose? We could use the pivot point here at the wheel. That would be the first one that comes to my mind. But in fact, if we take it about the center of the mass of the load and the wheelbarrow, we can in fact neglect the contributions of these two forces. So our expressions simplify a little bit. So let's do that. So let's evaluate the torque about that one. So in that case, in positive direction, we have FL times, how far is FL from that point? It's 1.4. Okay, let's call this L2, and that's L1. So that's then going to be, that's misleading. So here we have L2 minus L1. And then the only torque is that of the support force N, and that is in the negative direction, and its lever arm is L1, and the net torque must be also 0. We have two unknowns, N and weight of the load. So from this equation we can in fact solve for the support force N. That's going to be FL times L2 minus L1 divided by L1. And the maximum value for lift force was 650 newtons. The difference between L2 and L1, that's 1.4 meters minus 0.5 meters divided by 0.5 meters, and we get 1170 newtons for n. And with that, we can solve the weight of the load from the first equation. So weight of the load then becomes FL plus N minus weight of the wheelbarrow, 650 newtons plus 1170 minus weight of the wheelbarrow, that's 80 newtons. And that gives us total 1740 newtons for the mass of the load. So we see that the amount of load we were able to lift almost tripled. And the question is, where does the force come from that enables you to lift more with the wheelbarrow? We should look at this here. So as we can see, the force FL gets multiplied by this relationship that in general depends on the geometry of the situation, but it's called the principle of lever arms. So if we lift further from the pivot point, we get more torque for the same force. Of course, nothing comes for free, so there is something that has to bear the extra weight, and in this case it is the support force from the wheel. So that has to be able to carry a load of almost 1200 newtons, and that has to be taken into account in the construction of the wheelbarrow, and in general case in the construction of more critical items like buildings and bridges.